So more about fluids and pressure. Let's think of this. Here's some kind of fluid, and imagine some object is immersed in it. Keep it simple. Let's just say it's a cubic shaped object. In the dimension of d meters for all three dimensions of the cube. So the volume, of course, is d cubed. Let's think about all the forces on that object. There's the weight pulling down, and there's one more downward force. There's pressure on the top side. That pressure on the top side is causing a force that also pushes down. So we'll call it force from pressure on the top. And then there's an upward force. On the bottom side, there's also fluid pressure, and that's pushing up. Force from the pressure on the bottom. Remember one important point that is made in the text. You saw this in the reading. The molecules in a fluid are bouncing around in all directions, and as a result, there's pressure from the fluid pushing in all directions. But sometimes the fluid molecules might collide with the bottom of this cube, and then they rebound. As we thought about yesterday, every time a molecule of the fluid collides, that's a tiny little force from the fluid on the block, and the grand total result of all those little collisions is pressure pushing up from below. Okay, now let's think about these two forces, just the net force from the fluid. That's just all the force pushing up minus all the force from the pressure pushing down on the top. Okay, this force, of course, comes from pressure. Remember the basic definition of pressure: force divided by area. So if we know the fluid pressure at any depth, we can figure out the force on any area at that depth. This is just the pressure on the bottom side of the cube times the area of one side of the cube. That's just going to be d squared, minus pressure on the top side of the cube times the same area. It's a cube. All sides have the same area. Now let's think about this pressure on the bottom. Let's say the top is a distance h meters below the surface, h meters into the fluid, and then of course the bottom surface here would then be at a distance h plus d below the surface. So use our equation for fluid pressure, the thing we found yesterday, and that's just density of the fluid times g times how deep you are in the fluid, which is h plus d. And then minus pressure at the top times area. forget the area factor. Minus pressure at the top. Use the same rule, that density G depth. So same fluid density, same G, and then how deep you are at the top surface, that'll determine the pressure on the top side, and that's just plain H. And then times area. So here we have if we do the distributive rule on these two things, one term that we come up with is density G H area. And here we've got minus density G H area. So those two things cancel out. And now what are we left with? We're trying to figure out the net force on the block coming from the fluid, and that's now just equal to what's left of this equation. So net force from the fluid is just density of the fluid, G times D, right? The term here with H was canceled out by this, and then times area. But the area of any side of this cube is just D times D. So D times D times D is D cubed. That's the volume. That's the volume of the cube. So what are we left with? The net force is just density times volume, density of the fluid times the volume of the cube. Density times a volume is going to be a mass, and a mass times G, that's a weight. So the net force from the fluid, this volume here, think about it for just a minute, that volume is the volume of the cube, but that much volume is the volume of fluid that had to be pushed aside to make room for the cube. In other words, this much fluid, this volume of fluid was displaced, moved elsewhere to make room for that cube. So density times the volume of water displaced just gives us mass of however much fluid was displaced. Times G, or that's just the weight of the fluid displaced. And we have a specific name for this net force from the fluid. We call it a buoyant force. Usually refer to it as F with a subscript B. And the basic idea, the important idea from which everything else evolves, is that when something is either immersed in a fluid or floating on top of some fluid, there's always a net force that points up, a net force from the fluid pointing up. And the magnitude of that force is equal to the weight of the fluid that was displaced. Right? We know that force must point up because that force is a combination of downward force on the top of the cube plus upward force on the bottom of the cube. But down here on the bottom, you're at a greater depth, so pressure is greater. And because pressure is greater, you've got a bigger force pushing on the bottom side than you have on the top side. So the upward force pushing on the bottom is bigger, the downward force pushing on the top is smaller, so the net result of those two is upward force, and that's the buoyant force. Let's just look at at a couple examples here, thinking about buoyant force. Let's say you've got just a block with a volume of 200 cubic centimeters, and then the mass of that block will be, let's say, half a kilogram or 500 grams, however you want to say it, and it's immersed in some kind of fluid. Okay, so what are the forces acting on that block? There is, of course, weight, pushing down, and then there's a normal force from the bottom of this container, pushing up on the block. And there's also a buoyant force because it's immersed in water. Right? We imagine that there's just enough space for a little bit of water to get in under here between the bottom side of the block and the bottom of the container. So that's enough for there to be upward force from the water here on the bottom side. So a buoyant force acts on that cube. Buoyant force always points up. And if this block is just sitting there at the bottom of the container, just sitting there means it's got a constant velocity, constantly zero. And of course, constant velocity is the same as saying no acceleration. According to Newton's second law, no acceleration means no net force. So all these forces, since they add up to the net force, all these forces have to add up to zero. In other words, we take all of the upward force minus all of the downward force. That all has to come out to zero. And that's enough information plus this to figure out exactly how strong that normal force is. Just rewrite this equation, and we've got normal force equals mg minus the buoyant force. Right? That is the normal force that's pushing up doesn't have to be as strong as the weight. It's less strong than the weight because the normal force is getting some help from another upward force, the buoyant force. So let's figure out what we've got here. And remember, when we're talking about fluids, it's usually convenient, sometimes just plain necessary, to rewrite mass as a density times a volume. We don't have to do it for this mass because we're told what the mass is, 1/2 kilogram. So the normal force is, first term there is mg, which is 1/2 kilogram times 9.8 meters per second, and then minus the buoyant force. Remember, the buoyant force is the weight of fluid displaced. In this case, let's say the fluid is water, plain old water. Just to keep things simple. So the buoyant force is the weight of water displaced. Weight is mass times g. So the buoyant force is mass of water that's displaced times G. So let's take this to the next step. 1/2 times 9.8 is 4.9 newtons of force minus mass of the fluid displaced, water in this case. Mass, let's write it as density times volume. So density of the fluid times volume of the fluid displaced times G. But of course, the volume of fluid displaced is the volume of this thing, because this is the thing that did the displacing. Enough water had to be displaced to make room for something with a volume of 200 cubic centimeters, so 200 cubic centimeters of water were displaced. So now we've got enough numbers to figure out this term, and that'll tell us exactly what the strength of the normal force is. So normal force is 4.9 newtons minus this second term, and the first factor there is the density of water. You can look that up in the beginning of chapter 13, and you find that the density is 1,000 kilograms per cubic meter, or 10 to the 3 kilograms per cubic meter. This number is in newtons, so this other number that we're calculating has to be in newtons also, in order to ensure that our value for the normal force is in newtons. And if you want newtons, you have to use kilograms, and you have to use meters. You cannot use grams or centimeters. So next term then is the volume, which is 200 cubic centimeters. We have to convert that to cubic meters. So 200 cubic centimeters, or write it as 2 times 10 to the 2 cubic centimeters. We'll convert that to cubic meters, and the conversion is that 1 cubic meter is equal to 10 to the 6th centimeters, or 10 to the 6th cubic centimeters. Or 1 cubic centimeter is 10 to the minus 6th cubic meters, either way. But do the math there, and now we've got 2 times 10 to the minus 4 cubic meters for the volume. So volume is the next term. 2 times 10 to the minus 4 cubic meters, and then the last term is G, the usual 9.8 meters per second per second. And since here we've got a unit label of meters cubed, and here we've got a unit label of meters cubed in the denominator, treating unit labels as if they were algebraic variables, this is canceled by this. And so we're left with 10 to the 3 times 2 times 10 to the 4th, so that will come out as 2 times 10 to the minus 1. So in that second term there, we got 2 times 10 to the minus 1 kilograms. So that's the number we got from multiplying density times volume. Density times volume always gives you a mass, times 9.8 meters per second. And so this, which you can think of as 0.2 times 9.8, gives us minus 1.96 newtons. And this term was 4.9 newtons. So then the actual normal force is 2.94 newtons, or rounded to just plain 2.9 if you like. Okay, let's try a different situation and see how our understanding of buoyancy helps us with that. Now imagine a bunch of things that are all floating, and there are say 4 different objects. Just to keep it simple, let's say they're all rectangular objects, but they're different sizes, different masses, different weights. And as it turns out, they all displace different amounts of water. They're all floating, so they're partly above the surface, partly below the surface, and different amounts below the surface. There's A, B, C, and D. Okay, they're all displacing different amounts of water. And remember, the strength of the buoyant force on these things is just equal to the weight of water displaced. Well, this displaces more water than any of the other ones, so the weight of water displaced here is greatest. So the buoyant force on this one is strongest. And that tells us something, that they're all floating, so they're neither rising nor sinking. They're just staying put, again, just like in the previous example, a constant velocity of 0. So we can say all the same things. Constant velocity means 0 acceleration. 0 acceleration means no net force. So the forces on each of these objects has to add up to 0. But on each object, there are just 2 forces. The upward buoyant force and the weight pulling down. Since the net force is 0, that means that these 2 forces have to cancel out to give us a net result of 0 net force, which means for each of those objects, the buoyant force is just as strong as its weight. The weight of the object. And remember, this is always weight of the water displaced. A bigger weight, a heavier object, has to displace more water in order to float. So if we were ranking by the strength of the buoyant force on each of these things, it would be just the same as ranking by the weights or masses of those 4 things. Like that. Now, one important fact about floating, because if things float, the buoyant force and the weight of the floating thing are the same. Mass of the object times g, that's the weight of the floating thing. And again, let's do the same thing. Let's write masses as density times volume. Right? This is the mass of the fluid displaced times g. Like buoyant force is the weight of fluid displaced. And then this mass is density of the object times volume of the object times g. There's a factor of g on both sides of that equation, so they can cancel out. Divide the whole equation by g, and those g's disappear. Now let's write this as a density times a volume. Mass of fluid displaced is density of the fluid times the volume of fluid displaced. But how much volume of fluid is displaced? Well, what displaces the fluid in every case here is just the however much volume is under the surface of the fluid. Right? For thing A, right, this much volume of fluid is displaced. For thing B, this much volume of fluid is displaced. Likewise for thing C, this much volume of fluid is displaced. So the volume of fluid displaced, we can give that another name, because the volume of fluid displaced is just equal to the volume, however much volume of the object is underwater or under the surface of the fluid. So let's write our equation this way. Density of the fluid, volume, the volume submerged, however much volume of the floating object is submerged, and that's equal to the volume, to the density of the object times the whole volume of the object. Now, divide both sides of the equation by volume of the object, and then divide both sides of the equation by density of the fluid. So now, on the left-hand side, we've got just volume submerged divided by the total volume of the whole object. And here on the right, we've got density of the object divided by density of the fluid. Well, if the object is floating, then there's at least a little bit of it that's above the surface of the fluid. So if the object is floating, only some fraction of the object is beneath the surface. That is, the volume submerged is less than the whole volume of the whole object. So if there's floating, this fraction is less than 1, which means if there's floating, this fraction is less than 1. So floating means this fraction is less than 1, which means the density of the object must be less than the density of the fluid. That's the condition for floating. Anytime you have something floating, that's always the case. The density of the floating object is less than the density of the fluid. Ice floats in a drink because the density of ice is less than the density of liquid water. So that condition is satisfied, so there's floating.